Hello everyone, my name is Prohim Tem, who is a master candidate from Department of Software Conversion in Sun Yat-sen University. Today I would like to present about SDN Neural Network Oriented Controller in Internet of Things and Big Data Computing for effective quality of service control. In this topic, we will go through five main content. So let's get started with our topic introduction. So we would like to illustrate this figure. We would like to illustrate about the 5G communication network, which consists of multi-cell connectivity, such as massive macrocell, massive microcell, femtocell, and picocell, and relay. So based on this massive connectivity, it makes the network traffic quality control a challenging drawback to overcome, and we need a solution to manage it efficiently and intelligently. So to handle this scenario, the proposed solution has to be dynamically decouple the control plan and data plan, flexibly cluster each traffic condition status, and ensure the big data control with high volume, variety, and velocity. So to enable all these requirements, we will use a famous paradigm that be able to separate the network control and forwarding layer, which is known as SDN. And we will divide the data plan and control plan and application plan and provide a programmable and scalable architecture to centrally manage global view of the network with open flow controller. And in terms of open flow controller, we can use any operating system. It can be Rio, Knox, or Open Daylight. And the next is to construct an intelligent controller. We require to implement machine learning algorithm that is highly used for compiling, fitting, modeling, clustering, and recommending over training and testing dataset. And furthermore, we can cope with massive data transmission and receiving continuously by handling the big data management for pre-processing, cleansing, transforming, integrating, analyzing, and visualizing evaluation. So we believe that based on these three main related work, we be able to provide many supportive functionality toward a self-orchestration and big data computing and adaptable neural network oriented controller configuration. Next, main related work is the neural network and big data tool. So in multiple connectivity with massive IoT device, we have to be well prepared for big data management as well. So in term of supervised learning algorithm, we select neural network, which is be able to deal with the network performance and different QoS requirement in 5G network. So it is been proposed to learn the network scenario and generate a predictive output to reach the level of QoS assurance. So in this study, the algorithm are trained by the historical QoS dataset and anomaly. Then the supervised machine learning algorithm, also called neural network, will generate a new learning state to rebuild or reconfigure the optimal action for predicting the possible anomaly in the future and classify each quality of service group more accurately. So the next is that how we can handle the big data, big IoT data set. So we will use some tool such as Apache Hadoop, Spark, and Zeppelin in our edge server, also baseband unit tool. So let's move toward our proposed framework. So the first, in this proposed framework, we use three main related technology as we have previously discussed, and then the proposed controller is built for effectively controlling the QoS requirement, differentiation, and in that we will start with the dataset pre-processing. Toward the end goal, we will be able to cleanse and our dataset, IoT dataset, to to a well organized and well adjusted uh, dataset flow, such as delay, channel status, packet size, packet error ratio, jitter, PDU size, or even priority code. So after we have this clean data, we'll be able to apply our supervised learning, which is a neural network algorithm that we select. In step toward our end goal, we will start from initialize the IoT dataset input, and the next one we will define the general and target feature based on the QoS requirement that we imported from the application service, and then we will split the dataset into the training and testing. So we will set the random state into 40, so that we will keep the training and testing splitting consistently, and then we will create the classifier based on ReLU activation algorithm and Adam solver method. And then we will fit the classifier to our IoT training dataset. And after we fitting the classifier with our IoT dataset, we will be able to training our neural network model. So along with this training, we will set our error equal to 0, which means that at the first layer there is no error yet, but in each hidden neuron, we will try to append it to our preset value, so that we will know the total amount of that error. So every hidden neuron will be appended with the error. So if we reach the output layer, at that stage, if we be able to reach our output layer, we will check that starting error and the final, or we call it target error. But if we not reaching our output layer, we will keep going back to each hidden neuron to calculate, to inspect each condition first. And the next step, if until we reach the output layer, then we will compare between the starting error and the target error. If we can receive acceptable error, we will move toward our network model and we start to implement that model. But if we not receive and certify error or acceptable error, we will keep going back to the training step, which means that we keep changing the model. So if the condition is acceptable, we will end this neural network, and the final result we will receive amount of class that we recommend based on the target feature that we imported. So in the final step is the real controller configuration. So in this part is that we try to configure the forwarding rule, condition status, and requirement parameter based on the step 2 result. And this step we also call it neural network oriented controller by using a RESTful API, or it is stand for representation non-state transfer application interface, by update the operation resource to the application plan, while OpenFlow controller is used to dynamically manage the data plan forwarding path based on the controller orchestration. And then the routing optimization, load balancing, or fault tolerance for each QoS service are improved accordingly by the proposed controller. So in this controller, we will mainly focus on the setting forwarding flow, the real RESTful API script that communicate with the application plan, and the QoS control or condition setting, and the flow entry rule that we set to our data plan. So how can we possibly achieve all these performance steps is by selecting your controller operating system. We can trigger all these possible library to help us in this proposal. And the next one, after we finalize our controller configuration, we will evaluate our result. So in order to calculate the latency in this topic, we will use iPuff to trace, and then we will sum every time consuming, such as the time transmission, time propagation, time control in the control plan, and time neural network that we execute our machine learning. And for throughput, we will calculate by the total amount of bandwidth multiplied with the efficiency transmit by divided between the time transmission over the overall latency. And for packet drop ratio is equal to the packet loss and the packet transmitted. We will receive a percentage of the packet drop. And for the delay, we will sum every delay that exists in this topology, such as the delay of processing, delay of queue, delay of propagation, and delay of data transmission. For the jitter is the time difference between each packet sequence. So we assign it to dpic variable, and then we will sum it with the two and multiply with r. So r is the Gaussian jitter, or we call it random jitter, and n is the based on the bit error ratio. So based on this metric, we will be able to evaluate our performance compared to the conventional approach. If it is how much is it that it improved. So it's time for our conclusion. So by applying the conversion of SDN paradigm, real controller, big data computing tool such as Hadoop, MapReduce, Spark, and Zeppelin, and also neural network algorithm, to our proposed approach, the QoS control in massive IoT communication network can be well organized, classify, and effectively specify each service class requirement, and the converge technique give a variety of functional capability to perform intelligently and strengthen the various QoS performance conditions for a variety of service type. Thank you so much for your paying attention. And if you have any further question, we can contact me by this contact info. Thank you so much.